Hello, good afternoon. Welcome to our second machine learning for land modeling webinar. And today's talk is going to be more on the link between the physical land modeling and machine learning. And we would certainly benefit from the extensive expertise of our speaker, especially in the open community modeling, Dr. David Lawrence. Dave is a senior scientist at NSF NCAR and is currently serving as the chief scientist of the Community Earth System Model, the CSM. And prior to that, he was a co-chair of the CSM Land Modeling Working Group responsible to develop and apply the community land model. He's also the CSM Model Develop Liaison for the NSF Science and Technology Center project, named as the Learning for Earth with Artificial Intelligence and Physics, or in a short word, LEAP. So LEAP, for reference, is tasked, among other things, to bring machine learning to the community Earth system model. And that is actually one of the things that why David is here, besides his extensive expertise in the land modeling. But also Dave was co-leading the land use model intercomparison project. He's still leading that, actually. And he's the co-founder of the International Land Modeling Forum, the IMF. So for the discussion later, please use the Q&A section. And just for reference, that this webinar will be, the recording will be available in the ML4LM webpage. And over to you, Dave.
Great, thank you. Yeah, appreciate the opportunity here to talk to everyone today and give some perspectives on I guess, I'm calling the flexible interfacing of machine learning with land models, but really what do we need to do to, to bring machine learning and exploit machine learning to advance our land models and really Earth system models more generally through various mechanisms. And so hopefully I'll illustrate a few of the opportunities, challenges, and progress. So I actually want to kind of couch this in the context of a meeting we had a couple of years ago that myself and Eleanor Blythe hosted, called the Land Surface Modeling Summit, which was, I think, the first time that the group of land modelers around the world, international land modelers, got together to talk about the challenges that were being faced within the land modeling sphere, and trying to identify pathways forward, including machine learning. And the sort of the premise for that meeting was that land and Earth system models are increasingly being asked to provide information on societally relevant impacts and adaptation associated with climate and environmental change. Important things like ecosystem vulnerability and the impacts on the carbon cycle and ecosystem services, water and food security in the context of climate variability, change, and extreme weather, land-based mitigation solutions, needed to approach net zero targets, and the impacts of land use and land use change on climate, carbon, water, and extremes. Hazard prediction really involves a lot of the land surface process as well, and also understanding and exploiting the sources of predictability from land processes. And all these things are really critically important. And as we went through the meeting, at the end of the meeting, we had a kind of a summary discussion, and we said, fundamentally, that's a nice complicated way of describing it, but fundamentally, what we really need to know is, will there be enough water? Will we be able to produce enough food? And will we be able to produce that food sustainably? Where and when will people and ecosystems experience more extreme events? And where are we going to put the carbon if we need to pull the carbon out of the atmosphere onto the land or the oceans? And will it stay there? Obviously, it's one thing taking it out, it's another thing for that carbon to stay on the land surface. So I thought this was a nice way to sort of synthesize what we're doing all of this for, trying to develop land models. And land models are really important to address all of these questions, or system models in general, but land models in particular, to address these questions of societal relevance. And I think we're getting to the point where we have land models that are comprehensive enough that we can start to believe that we can reliably address these things. So many of you will have probably seen this figure before. It's created by Rosie Fisher, sort of in collaboration with a group of people. Looking at the history of land modeling, we started off as building
Sorry,
land models.
Dave. I'm not seeing your slide. I'm not sure if.
Oh, you're not seeing my slide? It says I'm sharing.
Okay.
Is anybody seeing it?
I'm not currently seeing it, but I could see it before.
You see it now?
Yeah, I can see your screen now. Yeah.
Okay. Sorry about that.
Sorry, it was I think it was only from my side anyway.
Okay. Yeah. Okay. Apologize if anyone missed the first slides. Okay. So the evolution of land surface modeling, when it started off by just needing to provide surface energy fluxes for atmosphere models, evolving into representing plants and soil moisture and plant functional type distributions, lakes, rivers, wetlands, dynamic vegetation, the carbon cycle, groundwater, land use change, urban systems, demographic vegetation, nutrients, crops and irrigation, lateral flow. So really complex array of processes. And as we evolved across the years, went from these, I like this analogy Will Weeder came up with originally about relatively simple models that we could sort of understand completely to bicycles that are weighed down by a bit more things to now quite complex, comprehensive, to the point where there probably is no person in the world who fully understands everything that's going on in the current generation land models. And there's a nice paper by Rosie Fisher and Charlie Coven that sort of outlines, what do we do with this challenge of representing complex terrestrial systems as we keep increasing complexity. And then a second paper led by Eleanor Blythe, talking about the advances in land surface modeling over the past several decades. So, I think, like I sort of said, I think we're getting to the point where we have tools that are available, but they're still not good enough in many cases, especially in our system modeling context, to provide reliable information for, say, policymakers. And here's just an example. I'm not going to dwell on this, but an example of a type of bias or error in models that makes them not useful. So this is looking at the actual science implications of the fact that ESMs do not accurately simulate hydrologic sensitivity. And so hydrologic sensitivity is the concept of if you have a change in precipitation or temperature, what is the change in runoff you get? And so on the curve here on the left, if you look at the interannual variability, this black line is the observation. So if you get a change in precipitation or a wet year, and this is for the upper Colorado River in the US, Western US, you get some amount of change in runoff. And it's, it's sort of a relatively linear relationship between precipitation and runoff. What you see is you look at all the Earth system models, they're all producing different, relationships between a change in precipitation and a change in runoff, implying that you can't really trust what is coming out of these models if you want to make a projection about how much water is going to be available on land. And so this is the kind of thing that we would like to be getting better to have more faith in our models. So at the Land Surface Modeling Summit, we had the goal of the summit was to identify collaborative steps that we could take as a community to accelerate progress, to resolve some of the big errors and biases, and to do things like managing the model complexity. And so we had a series of focal sessions. And the reason I'm sort of highlighting this is because these focal sessions are sort of ended up being the kinds of things that we need to do to also interface with machine learning. And in fact, we also had a machine learning session. So these focal sessions included, dealing with intense subgrid heterogeneity, managing the growing model complexity, building shareable code or modular code so that we could not all be reinventing wheels. This will become particularly important as we start moving towards machine learning-based parameterizations for models, issues with maintaining and developing input and forcing data sets, integrating humans into the system. That's a really complex part of the system. Benchmarking, which again is important for machine learning. Having good ways to evaluate and validate the models, machine learning approaches, and then parameter estimation and uncertainty. And so several of these topics are what I'm going to highlight today as the things we need to be working on to provide these interfaces with machine learning. And if anyone's interested, we have recordings of all the presentations that are available at the conference webpage. And so I've sort of couched this in the context of land models, but really the whole climate science endeavor is in transition. We've gone from building our system models to try to understand whether climate change is happening to these more urgent needs and more pressing and more difficult needs for actionable information. I've sort of already mentioned this on climate risks under different emission scenarios, the consequences of innovation mitigation. In addition to really understanding the risks of tipping points, I think continues to be a really important part of Earth system and climate science, and even more important as we have established that climate change is happening. Now we really need to have advanced warning of potential tipping points. And yet progress towards more accurate, reliable Earth system models remains frustratingly slow. As you go from one model generation to the next, while the models are improving, we've been able to show that the levels of improvement are modest, and some major systematic biases remain in our system and land models. So many people around the world are proposing that we move, that we take advantage of the explosion of machine learning and use that to try to advance, more rapidly advance your system models, including land models. And so this is a figure that came from a paper that I was a co-author on, led by Veronica Eyring, arguing for the need to build hybrid models. And I'm going to focus here on hybrid modeling. There are obviously other approaches, full model emulation, for example, that most likely will come into play. But from the point of view of this presentation, I'm going to be focusing on the advance of use of hybrid models. So just to be clear, if people haven't heard the term before, the idea is that we would either combine information that we know from high resolution kilometer scale or large eddy simulation or direct numerical simulation models in the atmosphere, the ocean, or the land if we had them, although we usually don't, with Earth observations to create new machine learning based parameterizations that can be plugged into Earth system models to hopefully accelerate the improvement of these models, get by some of these systematic biases that have been in existence, and hopefully the power of the machine learning be able to learn better the relationships between different variables and outcomes allows us to make a more rapid progress. And then in the broader context, you would still use and have large scale, low resolution ESMs when you can run large ensembles. You could then employ machine learning based downscaling or regional refinement to then potentially drive impact models, and along the way then build the capability to to provide these more accurate climate projections. And LEAP, this project that mentioned in the introduction that I'm involved in, is one of these activities in the CSM world. We are trying to take a leap forward in reliability, utility, and reach of climate projections through synergistic innovations in data science and climate science, basically harnessing machine learning and data to transform VSMs. So this is what we're trying to do. Some people, I just want to put this in the bigger context. There are people around the world who think that moving towards kilometer scale models is what we need to be doing. And I do feel like that should be part of the equation. But we argue that we're fairly long ways off before we're going to be able to rely just on kilometer scale models to provide all the understanding we need to understand the climate change problem. And part of that is because we know that there's long time scale Earth system feedbacks and processes that we need to represent, and we're going to need these lower resolution ESMs for the near term to continue to study this. So this is a figure that sort of shows some of the potential opportunities that we came up with in the process of writing this paper, where machine learning based parameterizations may be able to replace existing parameterizations within the Earth system models. And I'll just focus on the land. There's opportunities throughout the system, and this is an incomplete list, but on land, and maybe this was covered in the first webinar, but there's many opportunities in the terrestrial carbon cycle and phenology, in land atmosphere interactions, flux exchanges at the land surface, replacing some of the older theories. Wildfire is another great example of a really complex process that doesn't necessarily have a lot of theory behind it, but there's a reasonable amount of data that can help understand relationships. There's opportunities in hydrological processes. I think there's really strong opportunities to understand that permafrost, climate, carbon feedback, and especially the abrupt, rapid change processes that are sub-grid scale and completely unresolved in current or system models that has potential to be used. And there's many others. So I think there's fairly clearly some opportunities. I just want to reemphasize here that in the atmosphere and the oceans, there is the opportunity in some cases to draw on really high resolution or high fidelity models to help build these parameterizations. On land, I don't think we really have that capability as well. We do have some models that are quite process rich, but they're still using many parameterizations. And therefore, we're sort of restricted on the land side to opportunities where there's, I think, sufficient Earth observations to be able to develop a machine learning based parameterization. I'm happy to be corrected about that, but that's my current perspective. Nonetheless, there's plenty of opportunities. So how do we get to be able to be able to employ machine learning and based parameterizations in current generation land models? Yeah, so what is needed to realize and accelerate the potential of ML to improve land modeling? So coming back to the Land Surface Modeling Summit, coming out of the Land Surface Modeling Summit, we sort of found the need for more international discussion and interactions. And so we created this thing called the International Land Modeling Forum, which is mainly a way for groups to share ideas, relevant workshops and meetings, advertise job opportunities, and coordinate different working groups that could form to tackle some of the most persistent problems. And so two of the initial working groups that were formed focused on some things that are quite important for this machine learning realm. And one of those is shareable modulars or developing modular code bases, and the other is parameter estimation. The third one was on the challenges of integrating humans. And the fourth one is benchmarking, also quite relevant to the machine learning endeavors. So if anyone wants to join the ILMF, here's a link. And so what we did in 2023 is we had a series of webinars, kind of like this one, although in this case they were a little bit more discussion oriented, focusing in on these initial focal topics. And I just want to kind of highlight, and particularly for this shareable modules one, some of the things we talked about during that session. So I think, coming to this question, what is needed to realize and accelerate the potential of ML to improve land modeling? I think clearly more accessible and modular code bases is one thing. So on the left here is an image just of what would look like a really poorly written code that you can't understand, which is probably slightly true of many of today's land models. These land model code bases are very large, they're very complex, and have legacies of 20 plus years. They have hundreds of thousands of lines of Fortran code. I think CLM is approaching 400,000 lines of code. It's Fortran code, which of course machine learning experts find unpleasant at best. The code is tangled code webs with lots of technical debt. We have a long history of postdocs and graduate students and research scientists trying to develop these codes, many without software engineering expertise, building up, doing the code development in ways that may not be sustainable in the long run. And we're done with deadlines and things like that, leading to these tangled code webs. And my perspective, I think the perspective of a lot of people, is that this code complexity and actually the fact that we're in Fortran can be a barrier to entry for those who are interested in machine learning, or really any early career scientist who's really learning about things like Python, obviously. So how do we address this? Well, one way to address it would be to try to convert the code into a Python-based language. And it does look like that is possible, that there are ways with Python backends to make the code fast enough, but it would be really costly. We've done some cost estimates of what it would take to convert all of CSM, so a bigger activity, and to Python or a Python-based language, and our estimate an optimistic estimate was about 100 people years of time to convert the 2.5 million to 3 million lines of code in CSM. So it's a little bit impractical to think about how to do that, at least in the near term. But cleaner, more modular code, I think, will help and maybe get around some of these issues. And if the user doesn't need to know all the details of Fortran, maybe it won't be so difficult. So one thing I think is important to do, and I think all the groups around the world are doing this, is code refactoring. And so this is a slide credit from Bill Sachs here, where we had an issue in the community land model where we were doing things like calculating a flux, say a water flux or an energy flux, updating a state, calculating another flux, and maybe a third flux, and then updating another state, and kind of it went through, and it was sort of written in this sort of sequential mode, and it was hard to understand because the flux updates, flux calculations, and the state updates were all interactive, sequential in the code, and it wasn't easy to see how everything was adding up all together. So we've done quite a bit of work within CLM to resolve that and sort of moving towards this framework where you have a situation where you calculate all the fluxes you need to have, and then update the states as a following step. It's the kind of thing that you would have done from the start if you had been building the model from scratch now, but these models were started to be built 20 plus years ago when things like object-oriented code bases didn't even exist. And so then we also have the capability then to select different options for different flux calculations, object-oriented code, and different options for flux 2, and maybe this could become a machine learning based option, and becomes fairly straightforward to plug in when the framework is built like this. And so the benefits of this code refactoring is it partitions the complexity. It's easier to plug in alternative parameterizations, including machine learning based parameterizations, and the separating of flux calculations from state updates allows other advanced things like separating the physics from the numerics, and adding things like water phase shifts and isotopes. So I think this code refactoring is an important feature, and hopefully groups around the world are working on similar kind of activities to make cleaner code bases. It also reduces chances for introducing bugs. And I like this analogy that Bill Sachs put in here is that this was the code base maybe prior to this effort to refactor the code. That it totally mess. It's a dirty kitchen. And then we might get to this. So we're not going to get to the point where we're going to have the really clean code base where everything is really easy to track and follow, and it looks like like a penthouse kitchen in New York, but it will be something you can live in at least. And I think we've largely gotten there within CLM. So within the context of the International Land Modeling Forum, these webinars we had a series of talks. I'm just going to highlight a couple of things from those talks about modularization and shareable modules. That there's a fairly wide agreement across groups that would really be ideal if we could share code modules across land models, so that we are not all essentially reinventing wheels. And so Martin Clark, who's really been a proponent of this shareable module concept, gave a presentation, and he was putting the problem context here is in the glut of hydrological models. He's a hydrologist, so hydrological models and land models are largely synonymous. In many cases, there's more models than there are algorithms to populate them. So the challenge then is, can we define a general master modeling template with general design principles from which existing models could be constructed? That would be the ideal if we could possibly do that. So the challenge is, can we unify the model building blocks across multiple levels of granularity? And it's complicated. There's many different ways that we're already doing this. There's obviously multiple land models out there. There's some models that are sharing parts of code already, or model extensions. Some models have model components that are pulled out enough that you could potentially share them. Some models have multiple parameterization capabilities. And asking this question, can we thread this complex needle between multiple models that work together in the same framework and multiple parameterizations that work together in a plug-and-play framework? The other issue is complexity. And here's an example related to this model that's called the Functionally Assembled Terrestrial Ecosystem Simulator. So this is a next-generation vegetation demographic model that's been developed by colleagues at NCAR, DOE, and Norway. And FATES is this a demographic model for anyone who's heard about that. It's modeling vegetation cohorts separately and allows you to track age and size distribution more reliably and model vegetation response post disturbance in a realistic way. This is just the animation on the left, just showing the disturbance related to fire and the regrowth after that. Within FATES, we've spent quite a bit of time trying to work toward this modularity concept. And so focus on this process level modularity that I mentioned earlier. So allowing, within each say flux parameterization, allowing multiple different options, including potentially a machine learning based option if there was one, splitting the model up into little bits and pieces, getting closer to this ideal modular code that you would want to have. So that's, promising step forward. But the model has gotten way more complex now. And so if you're a new person coming in and trying to bring machine learning into this even more complex model, it may become, way overwhelming. Even spinning up the model has become a massive challenge. And so at the same time as building in this modularity, we also build in this ability to, create more simplified versions. And so let's say, for example, you had a machine learning based parameterization for some hydrology process. You could start off with this simplified model for catchment hydrology, which is sort of ignoring most of the complexity of the FATES model, but allowing you to test your parameterization in a more constrained situation where the plant physiology is relatively constrained. And then you can step through varying levels of complexity if you want to. So that's another important thing that I think we need to be considering as build models. So one of the summary talks was this there in that particular session, how do we move towards modularization and land surface models? And really, this is about as far as we got. As we identified there's two possible pathways for international collaboration. The first is a top-down approach where we get together and define generic modules and standard interfaces. That could be quite hard to do across multiple modeling centers. The second approach is bottom up and say, let's take a particular subroutine module that we think would be amenable to pulling out, in this case, leaf phenology, which is also quite amenable to machine learning, and try to see if we can create a module that could be used by many groups. And this is about as far as we got. This really requires funding, and it's hard to find funding to work on these international projects. Okay, but nonetheless, I think most likely, I don't think this is a huge stumbling block for machine learning, bring machine learning in. I think most models probably are structured well enough now that you can do it, relatively straightforwardly. I will stress one thing though, is that to bring machine learning into an Earth system model in general, into a land model in particular, ideally you would have some way to bring all the advanced tools from something like PyTorch, Python-based tools, machine learning, the rich array of machine learning-based tools that are available in something like PyTorch into a Fortran-based model like the community Earth system model. And one option is FTorch, and that's the one that we in the community Earth system model are currently exploring and probably adopting to do that. And this is an important step in the whole process, and I'm sure different groups around the world are trying to figure out how to do this. But having this robust and flexible implementation really requires this Fortran Python bridge. So just doing it once is fine. And we have an FTorch implementation that seems to be working with CSM and CLM fairly well, but that doesn't really help other people. We're hoping a large community of machine learning experts try to engage, and to enable broader use, it really needs an integration plan to bring it fully into CSM3 infrastructure with all the robust testing and edge case evaluations required, and really detailed documentation for how a user could employ it. And so one thing we're trying to push for is some consistency in implementation and documentation of such a Fortran Python bridge across modeling centers. So unfortunately, I think we're in a situation where everyone's going on their own. Ideally, we get to some more uniformity about that. Okay, but nonetheless, in terms of machine learning-based parameterizations, I think at least in the CLM world, we are ready to try to ingest machine learning-based parameterizations, and we do have several projects across the LEAP activity, which are trying to bring it. The first one and the most logical one being phonology, but I don't have any results. Okay, so then for the last 10 minutes or so, I want to talk about parameter perturbation. The other way I think we can really bring machine learning to advancing models. So we've been working on this activity for the last 4 or 5 years or so, and just want to really acknowledge that the work of Lenny Hawkins, Daniel Kennedy, and Katie Dagon, who have been leading the effort on the CLM side. But really, there's an international community of groups that are trying to really exploit machine learning to advance parameter calibration. And I'll get to a proposed MIP at the end of this that's coming soon. So the motivation for PPEs is fairly straightforward. The models are getting more and more complex. On the right just shows the massive complexity that's in a land model like CLM. And associated with that is an increasing number of uncertain parameters. CLM has more than 200 parameters in it. And in fact, many of those parameters have a plan functional type dimension to it, and we have 15 plan functional types. And so if you count the total number of actual parameters, independent parameters in CLM, it's probably over 500. So that's a lot of parameters to deal with. In the past, we've had to rely on, just using parameter values from the literature, direct from literature. And then when we're trying to calibrate the model, we've been relying on hand tuning. And that's obviously not a sustainable practice. It's really difficult to diagnose structural improvements. It's because it takes so long to do the hand tuning. It's challenging to incorporate new parameterizations, including machine learning-based parameterizations. It's impractical. There's an impractical requisite knowledge base. There's only a few people in the CLM world who know how to calibrate the model, and it doesn't scale well with increasing model complexity. So obviously, we need to get beyond this hand calibration. Additionally, we're certain that parameter uncertainty has a large contribution to the total uncertainty. And on the right is just showing this, off-shown figure of the cumulative land carbon flux, which is, really important in the overall climate change uncertainty. And it's a huge uncertainty across land models. And we don't know whether that's coming from structural or parametric uncertainty. It's almost certainly coming from both. And this is, probably the second biggest uncertainty in the climate change system after clouds. And so it's really important to help us understand how much of that uncertainty is coming from essentially the different parameter values that are being used in all the different models. And then finally, systematic parameter calibration would really enable and enhance the accuracy of simulations and increase the suitability and accessibility of CLM or land models in general for actionable science. If our models are not simulating reality with any degree of accuracy, no one's going to really trust them for use in actionable science. And furthermore, there's an unprecedented availability of Earth observations, huge array of satellite observations online now or coming online in the future. And then there's things like the Flex networks and the Neon Flex network, which provide this, really rich array of observations. And then finally, in this really important this realm is these integrated metrics packages like ILAM, International Land Model Benchmarking Package, which does a systematic evaluation of 35 land variables against 90 plus global, regional, and site level observational data sets, which really gives you a great way to evaluate your model. Either use this as part of your scoring system or just to evaluate your model post calibration. So in the CLM PPE project, there's several things we did. The first thing we did was we had to do infrastructure development. So several things we needed to do is to deal with the fact that it was essentially computationally impossible to attempt to calibrate the full biogeochemical version of CLM, which requires 1,000 to 2,000 year spin-up timescales, making it prohibitively expensive to calibrate a model if you need to run large ensembles of simulations. So we did two things. We did first a cluster analysis, and we were able to find that with about 400 grid cells globally, we could reasonably replicate the global simulation. So that really allows us to cut the costs on the model and have a fast model for relatively cheap. The second thing we did was a matrix solution to the carbon nitrogen states that decreases the spin-up timescales more than 10x. And these two things together allowed us to run fast enough that we could now run 500,000, 2,000 member ensembles for long periods of time, full historical simulations. We also had to expose all the parameters, pull them all out of the code. About half of our parameters were hard coded, which is obviously doesn't work if you're trying to do parameter estimation. Identify the parameter ranges for 200 plus parameters is a non-trivial job, and then building an ensemble analysis script. The first thing we did in the CLM world was we did a one at a time parameter ensembles under a range of environmental perturbations, and this is the kind of thing anyone would do if you're trying to approach a parameter perturbation problem. This is the first time we could do this in a fully coupled biogeochemical model. Fully integrated biogeochemical model and land model due to the computational costs I just mentioned. And so we ran control simulations for all 200 plus parameters at present day climate with high and low parameter values. But we also repeated those ensembles for 1850 climate and a future climate, and 1850 CO2 conditions and future CO2 conditions, and also in-depth additions. So this really allows us to assess not just the impact of parameters on present day land climate, but also on future land climate or responses. And so here's just an example of one of the reasons you would want to do that is you can then see which parameters are controlling the CO2 fertilization effect, not just the mean vegetation carbon stocks, but the fertilization effect on vegetation carbon stocks as you go into a future climate, and just see the list of parameters according to that. I'll say this has been really popular, just doing this simple one at a time parameter ensemble, and we've already got a large number of spin-off projects. And so I was maybe pleasantly surprised by how many groups were just using this first generation set of simulations just to help them in their own science. So then, can we then move towards parameter calibration? And we started this testing with the calibration of the leaf area index. And the reason we chose leaf area index is because it's a relatively difficult variable to calibrate. We didn't want to try something that was trivial. We'd actually started in a previous project by Katie Dagon, working on some in a leaf area index constrained mode. But also because the leaf area index is such an important variable controlling fluxes of water, energy, and carbon in the system, that it's the kind of thing you really want to kind of get pretty close to right in the Earth system model context. So we use that one at a time ensemble to identify the most important parameters for leaf area index, searching for parameters that control both annual mean maximum LEI, but also inter-annual variability, which control the responses to CO2 fertilization or climate change. And so came up with this list, and I think the interesting thing about this list, and these parameters won't mean anything to the people who are not involved in the CLM world, but they span a bunch of different parameter types: photosynthesis, hydrology, plant water use, phenology, physiology, respiration, allocation, nitrogen uptake, and snow. So that's kind of comforting to see that we're sort of hitting a fairly wide range of the model space. So then, you do what you would expect. You run a Latin hypercube, large parameter perturbation ensemble. You train your machine learning emulator. You confront the model with observational data. You can train this parameter space. You may find that you need to do some refocusing to zero in on the parameter space where all the action is, and then repeat this process. And we learned a few things along the way. We learned that we're better off if we try to train an emulator for each plant functional type independently, rather than for LAI at the grid cell level. That allowed us better performance, and we found we can generate pretty good emulators with high R-squareds and relatively low standard errors. It differed across vegetation type, but overall we were showing promise. So the general thing, you train an emulator for each PFT, you do the history matching process, you do the sample, you emulate for your parameters, you do a score cost function, you select your 500 best parameters. And what we're showing here on the right is that we were able to reduce the leaf area index biases quite substantially, going from the initial range, which is shown here in that light gray, to the target here, which is the observations, or what we are referring to as CLMSP, as our prescribed vegetation mode, which is based on observations. And you see that we are able to generate, within that ensemble, the constrained ensemble template would match observations for both these two different time functional types. In the interest of time, I'm going to skip over this slide and just get to this and say, we have been able to demonstrate that we can reduce the mean absolute error for leaf area index from over 1 down to, by at least half. And the places that are still in error tend to be places where there's agriculture. We haven't really treated agriculture issues very well yet. So this looks promising. It also looks like there's the potential to use these methods to constrain the land carbon cycle projections. And so this is showing all 500 ensemble members of the Latin hypercube of the cumulative land carbon sink over the 20th century. And so you see that over the 20th century, the land has been generally a source, maybe approaching a sink, mainly due to land use change in the early record and then CO2 fertilization towards the end of the record. And we see this range is about -200 to +50 petagrams across our ensemble of parameter predations, which is roughly the same as what we're seeing across all the land models involved in CMEP6. And so unfortunately, this has flipped the sign of this, but the range across CMEP6 models is -100 to +75 petagrams of carbon. And so, within our single ensemble, we can generate that range. And then if we're going out into the future, running CLM with atmospheric forcing from a CSM climate change projection, we see, that this can explode out to ±600 petagrams of carbon, which is as large a range as across all the CMEP6 models, just within CLM with our parameter perturbation. So the question then is can we constrain that with this history matching approach by just retaining parameter sets where there's reasonable values for observed quantities. So for example, on the left here showing, all the greens are the parameter sets that are giving reasonable values of leaf area index, and then what do you get for the carbon sink projection out in the future? And we can then use some other constraints, maybe the total land use flux or recent changes in live woody biomass. And I just want to illustrate quickly that if we use that leaf area index constraint, we don't see a big constraint in the total range over here on the right. If we start going to using the land cover change total carbon flux constraint, also doesn't provide a huge amount of constraint. But as we then try to use the recent historical sink constraint, we are seeing a restriction. And so this was really done in a really simple way. We didn't really do this in a systematic, comprehensive way, but it does indicate that we may be able to constrain our projections with this method. And my last point here is that there's still a diversity of carbon trend responses, but they're more constrained. And in an Earth system modeling context, we might be able to take this range of different parameter sets and build a set of Earth system models that we could then run in an ensemble framework to really understand, an emissions-driven, especially simulations framework, understand the consequences of this uncertainty in the land carbon sink. Okay, so the last 2 minutes or so, I just want to go through a few of the parameter estimation challenges, a really incomplete list, but things that we've come across along this process. One is, there's many emulation algorithms out there, and they exhibit differing performance, at least as you first apply them. And so there's Gaussian process regression, there's artificial neural networks, there's random forest, there's many others. We explored a few and just found quite wide range of performance. Now, we didn't go through the full hyperparameter tuning, and you might be able to get all these different algorithms to come up to the same value, but choosing the right algorithm is, how you do that is, I guess, for me, uncertain. We just, in the end, are choosing Gaussian process because it gave us the best at our first stab. There's challenges with PFT parameters. To reduce regional biases, you really need to be able to tune PFT parameters independently, but the number of parameters is huge. We have 10 to 15 PFT parameters and 16 PFTs. It's 300 plus parameters. That's a challenge. And also many observational data sets are not disaggregated by PFT. And so then you need to deal with that. How do you disaggregate the impact on a particular variable that's coming from multiple PFTs and then calibrate your PFT parameters with that information? There's another challenge is that parameter responses are not the same in coupled simulations to an atmosphere versus land only. And what this, the impact of these perturbations can be different, even exhibiting a different sign of response. And on the right is a figure from a paper that's reviewed by Claire Zarakas that shows that the atmospheric modulation of changes in ET due to a parametric change. And what you can see is where anywhere where it's like dark blue or dark red, the atmosphere is, when you put it into the atmosphere model, it's strongly modulating the impact of that parameter change. In the case of the blue, it's really depressing the impact, dampening the impact. In the case of red, it's amplifying the impact. So that's a pretty big challenge, which is hard to know how to address. And then just others, as you add constraints, new observations or variables and or new constraints beyond things like means and moving towards annual cycle amplitude and interannual variability trends, it is possible to likely that you cannot find reasonable parameter sets that meet all the constraints, probably highlighting structural errors in the model. So how do you deal with that? And then finally, calculating the whole model all at once is likely going to be impractical, especially as model complexity rises, especially in things like the full phase, full competition mode. And therefore, most likely, we need to develop methodologies to have what we call a calibration cascade, where you might start picking off pieces of the model and calibrating them individually and holding some things constant as you move and you step through the model complexity. So that's a lot. I'm going to stop there after I advertise this calibration land model MIP activity that's being led by Natasha McBean and others. And so this is a MIP because there are many groups around the world trying to work towards calibrating these global land models. We realize that everyone's taking slightly different strategies. We think there will be benefits to trying to evaluate these models against each other. So there's some virtual workshops coming up. I think they're closed, but look out for the reports on the impacts of these. I think it's going to be a really exciting project. So I don't have a summary slide. I'm going to stop here with this, sort of summary goal, which is to produce these hybrid physics and ML models to really leap forward in our reliability, utility, and reach of our climate projections. And I will stop there. Thank you.
Thank you very much, Dave. Great presentation. And I would have one question, and then I let you answer the QA. That's the advantage of being a panelist. So you showed the modularity slides and the importance of having modular setting. Do you think that all of the process could be modular? And if not, can we prioritize some process other than the other? And the second part is whether this, let's say, module or process-based module, in terms of machine learning, if we would like to have them as emulated, shall we have them like everyone separately that goes into application-oriented module, or shall we have them like all integrated together within, let's say, a whole emulator for the land surface?
Yeah, so I think, ideally, I think you can modularize the code and make every flux calculation modular. I don't think there's any barrier to doing that. It just takes time and extracting the code. And I think there's a lot of benefits to doing it. Even without machine learning, I think that we need to be doing this. So that's definitely a pretty high priority for us. But it takes a lot of time to get through everything. These code bases are bigger. I think it's important, and what we've also done is that everything new that comes in has to be modular, and that so going forward. The question about whether you want to emulate the entire land model versus emulating a specific process, I think they're two different tools, and I think we should be doing both. In some cases, emulating the entire land model, that will be really powerful. If you want to run really large ensembles, for example, you could really use that to run massive ensembles of your land model. You may be able to couple that into other emulated models and create this really, this potentially unwieldy, but coupling of different emulated model components. I think that groups are and will be working on that, and I think that's a way to go forward. What you lose with that is it being, I think, is useful a research tool. If we're trying to understand processes and only relatively rarely do we use these models to run these big simulations to make climate projections. Most of the time they're used to help us understand something about the system, and usually then you need to be able to dive in and control aspects of the model in different ways. And I think you've gone to a full model emulator, that's going to be more difficult. So I think we should be doing both. They have different applications. But I'm personally a little bit more excited because I'm more of a process-based person. I'm more excited about replacing the more problematic process-based parameterizations with machine learning-based ones, and seeing if we can really do better. I think right now it's a hypothesis that we can build a better model if we do this, and it's yet to be proven.
Yeah, thanks.
Yep. So do you want me to just go through?
Yes, please. Yeah.
Yeah. So I'll start with Matthias's first question. So one of the advantages of Fortran is you can still run your code 20 years later. Python code is not run anymore because the libraries change, and yeah, that is absolutely a big concern that we have. You know, is that it's hard enough to maintain a working code when, you know, even as they update small changes to compilers, for example, with Fortran, if you have a situation where Python is evolving and not staying static, that could become really problematic. So I don't really know how we get around that problem. I know we have people here who are thinking about it, but that is absolutely a concern going forward. One of the reasons why we haven't gone full bore into trying to do that. Okay, second question is, when calibrating models to improve performance for certain variables, there's a risk of degrading performance for others. How do you recommend resolving this trade-off? Yeah, absolutely. And now there's specific strategy or best practice to ensure a balanced approach that maintains overall model integrity. Yeah, I that is right. We have sort of seen so far with the leaf area index, partly because it was a variable that was so central to so many things, that if you calibrate that, we're seeing most things get better so far. But there probably would be variables where it would go off, and yeah, I don't know that we have a great solution to this. One thing you could do is to add that variable to your cost function, and so that you try to ensure that, you know, that variable you started seeing degrading performance is part of the cost function, and try to calibrate it. But as I mentioned towards the end, the more cost functions you add, the less likely it is you're going to be able to find some parameter space where it exists. So again, it's a difficult problem. What we're doing is evaluating, you know, we're going to calibrate for probably about 3 to 4 variables for CSM3, CLM6 for CSM3, leaf area index, GPP, ET, and vegetation biomass. And we think, and most likely just starting with mean values, and we think that's going to be hard enough. And then we will then run it. Once we then will then rerun the model, and we'll run through ILAM, and we will see whether or not we've really improved things or degraded anything really substantially. And if we have not degraded things substantially, that's great. If we have degraded things substantially, we may go back and do some light hand tuning to try to fix things. So I think it's going to be hard to get away from humans being in the loop. Maybe that's a short way of saying it. Second question from Matthias. You said, I have global maps that came from satellites. When I compare even the latest LA estimates from Copernicus, they were still only about half of what I measure on my eddy covariance site. How do I deal with biases and uncertainty in the observational data? Yeah, that's a huge. We just had a discussion about this at our meeting earlier this week. You know, one way we're doing it is to try to take those different observational data sets that exist and use that as our observational uncertainty. And so we're really not trying to get to to constrain to be targeting something too specific. So, you know, that's why in the slide I went by fast, but we're using a essentially expert judgment error bias of plus or minus 30% on the LAI as our target. So you could try to get more formal about that, but that's the way we're currently approaching it. Is that we're not trying to get too exact. We're just trying to throw out the primary sets, which are really so giving model simulations that are so far away from our central estimates of observations that they're completely unrealistic, but then allowing for a lot of parameter sets to pass. Now, how exactly we're going to choose one parameter set that we need to use in CSM3 is a little bit of a problem, and we're not really sure whether we can do a random draw, take the least error, or what. But yeah, hopefully I help answer it a little bit. But yeah, it's a big question. Question from Craig. Has the ILMF prioritized Earth observation needs, both land reanalysis and satellites, for this effort? Are there subgroups within the ILMF working towards weather versus climate applications? Different parameters and processes may dominate at different timescales. Yeah, so Earth observation needs, at least for the time being, what we're mostly doing is either using tower sites, which has the high resolution, temporal resolution, but not too many variables and not too much spatial representativeness. And we've been using the variables that have pulled into ILM. And those are our two things that we're currently doing. There is no uniform decision across modeling groups about what observations to use. In terms of weather versus climate applications, and also I mentioned just in the last answer, we're sort of using a relatively small number of variables at the moment because we know more variables you add, the harder and harder the problem gets. And so the bigger question is which set of variables are you going to try to target? I think, and we're going to pick the ones, in some cases, maybe that with the best Earth observations or the most novel Earth observations. I think every time you do this, you can make a different decision. And so one thing we're doing in the CLM world is we are trying to systematize this as much as possible so that every user could use their own set of observations, their own set of targets for climate or weather applications, their own set of parameters. Because there is no one answer to this question for sure. So having a flexible system is going to be really important. So I'm not sure if I fully answered your question, Craig, hopefully a little bit. I think we're getting close to the end of time here, so I'll try to move on. Depending on the quality of data used for calibration, the machine learning algorithm itself may prioritize certain variables over others during simultaneous calibration, potentially leading to trade-offs in performance. Yeah, absolutely. I'm not sure anything to say except for yes. With all these things, I will say my strategy, our strategy is do not let perfect be the enemy of the good. You know, what we've been doing previously is we've been hand calibrating these models. So we know that is not an ideal way to work, a systematic way to do this. And so if we can take a step towards it, even if it makes certain things not quite as good, I think we're going to be better off. And we're going to have to deal with this trade-off in performance and really decide what is the most important thing, right? And each model is one thing where each modeling group, each application may have a different set of priorities, which will define your decisions. Next question is, have you looked and thought about parameterizations that are not based on PFT? At this point, it's mostly thinking around trying to optimize PFT-based values only. No, we're not just optimizing for PFT-based values. We're optimizing for what we call the global parameters as well. Really, what you need to do is get Linnea, Daniel, and Katie to give a full-length talk about our full parameter estimation process. It's quite complex. And one point that I think it's important to note here is that there is absolutely no way a pure machine learning-based solution would solve this. It really needs machine learning-based expertise combined with domain expertise. We've been working on this for years now and coming up against problems every week. So it's really a rich and exciting, I think, area and I think that's one reason why this calibration MIP will be really interesting. We'll all be exposing our different methodologies to each other. Jafu, what are my thoughts about common funding sources? I don't have thoughts about common funding sources. Some of the foundations maybe can provide opportunities here to work across international boundaries. But those foundations, they tend to have restrictions that make it hard for modeling centers to really work with them to overhead. So I don't know how to deal with the funding source problem. If I did, we would have solved it. And then maybe last question from Matthias. Benchmark is great, but he's wondering if we all use the same benchmarks while model development is not benchmarking anymore, and we start introducing biases. One example is the Fluxcon estimate of GPP, which I personally think is about 20 to 30% too small. Yeah, totally. It's a big problem. My usual, a bit flippant remark here. Well, one thing is we need to be continually reevaluating our benchmarking data sets. That's something within ILM we talk about, is that maybe throw out the ones we really don't believe, or keep, you know, a wide enough range that we have that captures the range of hypotheses about what the true observations are. And that's a strategy. You know, some people are concerned about using ILM and the calibration process. We're not really there yet, but even if we were, I would just say these models are complex enough and it's a hard enough problem that if you can calibrate the model to match everything in ILM, then I would just say, give you a pat on the back and say, congratulations. I just don't think we're at the stage where we really need to be worrying about that. You know, this over-tuning is potentially a problem, but I'd be really surprised if anyone can actually do it. So I'll finish with, yeah, one effort is to improve calibration status, but parallel effort is further constraining the physically realistic parameter space. That's right. Yeah, everything here has multiple dimensions to it. So that's why I think, again, I think this calibration MIP is going to be really interesting to see what we learn from it. Because every modeling center that's trying to embark on this is coming across similar and probably unique challenges. And it's too big a problem for us to take on as individual groups.
Thanks a lot, Dave. That was a great presentation with great discussion. And yeah, I see that the last two questions were quite relevant to the next talk by Gab Abramovich about benchmarking. And yeah, thanks again for this nice presentation, and see you next time.
Great, thank you. Appreciate the opportunity. See everyone.
Thank you. Bye.